Okay, so good morning, everybody. So we're going to continue on with our lessons on oil heat, and today we're going to be getting into combustion. Combustion is a really important part to understanding whether or not a oil-fired piece of equipment is running efficiently. It is almost like as important as taking superheat and subcooling readings on a air conditioner or a refrigerator to see whether or not our refrigeration cycle is working at its peak efficiency. So really, we got to understand combustion. We have to understand what's happening in the process and what can cause issues with combustion. So as a technician, you have to make sure that that equipment is working at its peak efficiency level, no matter what. Okay, that's really what your name of the game is if you're getting into any sort of service in the HVAC industry. We have to understand the combustion theory and how to adjust our burners so that they operate at a safe, clean, reliable, and ultimately an economical operation. One thing we have to always keep in mind, first things first, is combustion is a controlled chemical reaction. Okay? Three things are needed in order for combustion to occur or to have fire. That is oxygen, you have to have an ignition source, and you have to have a fuel source. When heating oil is burned, the chemical energy in the fuel is converted to heat. That is what we're doing. We are taking those three things, oxygen, an ignition source, and a fuel, and we burn the oil. That oil being burned is now being converted to heat energy. The oxygen required for combustion comes from the air that is delivered by the oil burner fan. We have to make sure that the fan is running. We got to make sure the motor is running. Otherwise, we're not going to be able to deliver the air that is needed to our burn. The spark delivered by the electrodes provides the heat that is needed to start the combustion process. So where is that spark coming from? The electrodes. It's that spark that's giving us the heat. Remember, it takes about 600 degrees to ignite the oil. The heat from the spark vaporizes the oil droplets delivered by the nozzle, then lights the vapors on fire. So setting up an oil burner is really important, knowing that you're checking your electrodes, making sure the electrodes are set correctly and in the correct position, making sure they're far enough ahead of the nozzle, make sure the gap is correct. All those things is really vitally important in order for us to have a burn or a combustion process. If you take away any one of those, obviously combustion isn't going to happen. You're not going to have a fire. If you take away the air there, you're not going to have a fire. If you take away the fuel source, you're not going to have a fire. If you don't have anything to ignite it, you're not going to have a fire. You have to have all three in order for combustion to occur. Okay? So combustion is really a rapid oxidation of any material that will combine readily with oxygen. The resulting flame contains the hot gases produced when the hydrogen and carbon in the fuel react and combine with the oxygen in the air. Okay? This reaction creates light and releases large quantities of heat. For every gallon of oil, okay, it contains about 140,000 BTUs per gallon. Okay, so those that don't know what a BTU is, a BTU stands for British Thermal Units. The definition of a British Thermal Unit is the energy required to raise 1 pound of water 1 degree Fahrenheit. Okay? About the amount of energy contained literally in a birthday candle. You light a birthday candle, you put your hand over it, you feel the heat coming from that. That is about 1 BTU of heat. So 1 gallon of fuel oil, number 2 fuel oil, is equal to about 140,000 birthday candles lit up at once. Okay? In a typical oil-fired appliance, every gallon of oil burned is going to put out about 119,000 BTUs into the building. And about 21,000 BTUs of it is going to be lost. It's just going to go out the chimney. Okay? This is why oil is not 100% efficient. Because all of the heat that is generated by it is not necessarily used to heat a space. Some of that heat is going to be lost out the chimney. But if a furnace or an oil-fired appliance is set up correctly, it typically is going to put out, again, about 119,000 BTUs minimum. What's going to change that? That number. Orifices. Your nozzle size is going to determine how much BTUs that burner is going to be able to put out per gallon, 140,000 BTUs per gallon. So that nozzle has to be a 1.0. If it's a 1.5 gallon per hour nozzle, it's going to put out more than 140,000 BTUs, which is also going to change how much BTUs is going to be put into a building and how much is going to be out the chimney or out the stack. Heating oil is about 85% carbon and about 15% hydrogen. Okay, these ratios of hydrogen and carbon in the fuel combine with a specific quantity of oxygen to form combustion gases. So therefore, a precise quantity of combustion air is needed so all the fuel will burn completely. Too much air is going to lower your efficiency. Too little air is going to cause incomplete combustion and smoke and soot. So where we get into this is we have to understand how our fuel and our air react with each other. Okay, during the combustion process, new chemical substances are created from the fuel and the air. These substances, again, are called combustion gases. So when we have a hydrocarbon-based fuel, such as oil, and it burns, the exhaust gases are going to include water and carbon dioxide. Hydrogen, water. Combustion gases can also include carbon monoxide, oxide of nitrogen, or better known as NOx gases. And since sulfur is present in the fuel, sulfuric oxide can also be present when we are dealing with combustion. Obviously, we don't want a lot of carbon monoxide to be made when we are burning something like that. So that's why we have to make sure that the air and fuel mixture is pretty close to where it needs to be, because obviously we all know that carbon monoxide is a silent killer. Okay? We don't know that it's in the air until technically it's too late. So what is air? Well, air is 20.9% oxygen, 78% nitrogen, and about 1.1% of other miscellaneous gases. Okay, for every 1 part of oxygen, we get 4 parts nitrogen. Nitrogen is an inert gas. Okay, and most of it goes through the combustion process pretty much unchanged. So even after we're burning it, nitrogen is pretty much still there. It cools the chemical reaction by lowering the burning temperature, and it lowers the maximum heat content deliverable by the fuel. So therefore, it is impossible to achieve combustion efficiencies above 95% for most fuels, including natural gas. When air is used as a source of oxygen for the combustion process, that is something that is really, really interesting. You go and purchase a brand new, say, natural gas-fired piece of equipment, and they say it's like 95% efficient. That 95% efficient rating is coming from the laboratories that do all of the testing. That's a controlled environment that they do these testings in. But in reality, when that piece of equipment gets put into a home, it's a different environment. That furnace may not necessarily be achieving that 95% efficiency rating as they so lovingly put on their pieces of equipment. But as a technician, it is our responsibility to get that furnace up to the highest efficiency rating possible. That's sometimes not always the case. Oil is dirty. It's very temperamental. It has to be set in a specific way in order to achieve a high efficiency rating. And usually a lot of them are about 85%, maybe 85%, maybe some of them are about 90% efficient. That's still 10% of the heat that's being generated from that piece of equipment is going out the chimney. But again, it's our responsibility to understand how the combustion process works in order to get a furnace up to an efficiency rating as high as we possibly can. When flame retention burners, or if we're dealing with flame retention burners, some of the nitrogen combined with the oxygen is to form a nitrogen oxide, or NOx gases, NOx. Okay, it takes 14.4 pounds of air to burn each pound of heating oil, and we produce 15.4 pounds of combustion gases. Okay, if we could achieve perfect combustion, okay, another term for perfect combustion, if you ever wanted to sound like really intelligent, is called Storchiometric Combustion. Yeah, go ahead, say that word. But that's another really big term for quote-unquote perfect combustion. Each gallon of fuel oil consumed, you are going to need about 1,360 cubic feet of combustion air in order to achieve perfect combustion. And what we mean by perfect combustion, all of the fuel, everything is burned off 100%. Perfect combustion is very, very, very difficult to achieve in the real world. Can perfect combustion be achieved in a laboratory or in a controlled environment? Absolutely. Where we can control the amount of oxygen something gets and all that other stuff. Yeah, we can get close to perfect combustion. But in the real world, in a home or place of business, no. Perfect combustion is very, very difficult to achieve. So we always go for practical combustion. What's practical about it? What can we do to get it to as high as we possibly can get without having a constant burner being sooted up, damaged parts, and having to come back every other week or so and have to clean it and all that other stuff. Setting up the nozzle again, the electrodes, punching out the boiler, and all that other crap. Okay, so with 1 pound of fuel oil, we get about, again, we need about 14.4 pounds of air. And when we combine those two together, we get around 3.2 pounds of carbon dioxide, 1.1 pounds of water vapor, 11.1 pounds of nitrogen, and that's going to give us around 19,500 BTUs of heat. Okay, the actual amount of air that is required will vary by the heat value of the fuel and the design of the burner. Okay, heating oil contains roughly about 19,500 BTUs per pound. Non-flame retention burners need at least 1,700 cubic feet of air to burn clean. Okay, current burners that we are dealing with are about 1,500 cubic feet of air that is needed. We have to take in consideration building construction when we are setting up and thinking about combustion and how these burners are set up today. Because today, a lot of our newer buildings and homes are being insulated a lot better than the older ones. Okay, they're weather strippings. They're well insulated, and that's getting adequate combustion air to the burner is becoming more and more of a problem. In fact, a lot of our newer buildings today, especially newer homes, it's now actually a code. You have to bring in a certain amount of outside air into that home to help support the air quality in the home. Boilers are no exception. Furnaces are no exception. If that building is tightly wrapped and weather stripping and doesn't breathe very well, quote unquote breathe very well, we have to have some other means of bringing in some fresh air into that home. Because if we don't do that, it's going to make the home stagnant and have, air quality issues, but it's also going to screw up how our appliances work, whether that's natural gas or oil. When troubleshooting your combustion problems, you have to ask yourself those two questions that you see here. Where is my combustion air coming from? Where? Is it coming from my surrounding area? Is it in the room? Or do I have enough to burn all of my fuel? You got to get thinking that when you're actually looking at a burner or a boiler or whatever it is that you're looking at. You got to think about that. Because air is a big part of it. Do I have enough air? Okay, oil burner flames produce various combustion gases in fixed quantities. With perfect combustion, every pound of oil burned is going to produce 3.2 pounds of carbon dioxide, 1.1 pounds of water vapor, and 11.1 pounds of hot nitrogen. So combustion air supply and mixing and all that stuff, the better the air and the oil vapors are mixed, the better the burn or the better the combustion is going to happen. Burner air parts, including your turbulators, your spinners, end cones, flame retention heads, all that stuff, are designed to give good mixing of the atomized fuel droplets and the combustion air. In high pressure atomizing burners, such as your flame retention heads, several factors control the quality of air and oil mixture. The spray pattern of the oil droplets must be similar to the air pattern created by the burner. Flame retention burners have much better air and oil mixing capabilities than a lot of your older burners. New oil burners should not, and again, oil burners should not produce smoke. Okay, smoke and soot, which is nothing more than unburned carbon, are created by outdated burner designs and incorrect burner service and adjustments. Okay, smoke production is unnecessary and must be eliminated because it reduces efficiency and increases your service calls and is going to be a nuisance for homeowner, business owner, whatever it is. Okay, excessive smoke wastes fuel because it deposits soot on the heat exchanger surfaces. Just 1/32 of an inch of soot that is accumulated on a heat exchanger is going to reduce the efficiency of a piece of equipment by like maybe 2%. If we have an 1/8 inch of soot and deposits inside a boiler or a furnace in a heat exchanger, that can really lower the efficiency of a furnace by 9–10%. That's big. You're going to have issues. We need to make sure that our burners are properly set up and we have very little, 0 to a trace of smoke. And we will cover that in when I go over how to measure efficiency on these things. Okay, efficiency loss caused by a smoky burner occurs as the soot slowly builds up. Soot also affects the reliability operation of the burner. If it builds up on the CAD cell or a bimetal of a stack relay, for example, it can act like flame failure and cause the control to lock out on safety, creating an unnecessary service call. Now remember, a CAD cell has to see the flame. If the CAD cell is all sooted up and can't see anything, it's going to not see that light like it's supposed to. If you still have a stack relay, which is a temperature operated safety control, if there's soot that's built up on the bimetal of that, it acts as an insulator. It's not going to pick up the temperature correctly. It's going to cause problems. It's going to cause things to lock out. Unsafe. We have to make sure these things are working the way they're supposed to be. Overfiring can cause smoke. Okay? If a unit is overfired, the burner will create heat faster than the heating system can distribute to the building. You're damaging it. We don't want that. Okay? When this happens, the burner is going to short cycle, causing it to go on and off frequently, short periods of time. The problem is that older burners create smoke when they start and stop. Sulfur exists in varying degrees of all fossil fuels. Okay? The sulfur content in heating oil ranges anywhere from 0.5% to 0.05% by weight. When burned, sulfur mixes with oxygen and forms sulfuric oxide. It reacts with the water vapor in the combustion gases and creates sulfuric acid aerosol. Okay, and when that acid condenses, which usually is going to occur when if your stack temperature or your flue temperature is about 150 to about 200 degrees, it's going to adhere to the flue pipe and heat exchanger surfaces in a film and reacts with the iron in the pipe and heat exchanger walls. It's going to corrode stuff. It's going to break stuff. We don't want that. Scale buildup degrades efficiency by up maybe from 1 to 4% over the year. Okay, it also blocks flue passages, restricts airflow, and also increases your smoke and soot. It's really that important to understand what goes on when a furnace, especially oil, isn't set up correctly. Carbon monoxide, it's really a silent killer. If an oil burner is not set up correctly, it's sooted up and running like garbage, you're developing carbon monoxide. You're going to kill somebody. Okay, carbon monoxide, or better known as CO, is a toxic gas that can occur in homes and buildings where combustion byproducts are generated, not properly vented and allowed to accumulate. Carbon monoxide is a result of incomplete combustion due to unburned fuel. When any part of the flame is reduced below 1,128 degrees, CO will be produced. Okay, flame impingement also results in lower flame temperature and your CO potential. It is really good practice to have a carbon monoxide detector in the vicinity of your oil-fired equipment, your furnaces and your boilers. If there is any carbon monoxide buildup, that carbon monoxide detector is going to go off before it maybe reaches the rest of the home. It is really important that you put one in if you don't have one. Okay, we don't know it's there. We can't smell it. We can't see it. Okay? 0 parts per million, that's the desired level. Okay? 9 parts per million is the maximum indoor air quality level that is permissible. Okay, 50 parts per million is maximum concentration for continuous exposure in any 8-hour period. 400 parts per million, you're going to have headaches after 1 or 2 hours of exposure. It could be life-threatening after 3 hours of exposure. 800 parts per million, that's going to cause nausea, convulsions, death within 2 hours. 1,600 parts per million, that's going to be nausea within 20 minutes, death within an hour. 12,800 parts per million, you're dead within 1 to 3 minutes. Okay, very dangerous stuff. You want to make sure that your burners are working correctly. Okay, oil heat CO warning signs. If you see smoke near the burner, dark smoke coming from the chimney, or a smell of sharp raw oil smell, the burner is probably producing unacceptable levels of carbon monoxide. When you are looking at a chimney in the dead of winter, you want to see white smoke coming out the chimney. If you see black smoke coming out the chimney, that's a telltale sign that that bad boy is not operating correctly. Okay, next time you're driving down the road or whatever, take a look at the chimneys. If you see black, grayish smoke coming out, that furnace is not working correctly. Okay? Or not unless they have maybe a fireplace going or something like that, but that's a different, that's completely different. But if it's a boiler and you see that sort of smoke coming out there, yeah, that's a sign that that boiler isn't working right, furnace, whatever it is that's hooked up to that chimney isn't working right. Okay, CO is an odorless and tasteless. Therefore, in order to detect its presence, we perform combustion tests and look for other clues for combustion and ventilation problems. Again, such as a sharp gas or oil smell, stale or stuffy air, soot, rust, or scale buildup on or around an appliance and vent, loose or disconnected chimney or vent connections, debris or soot falling from the chimney, fireplace, or appliance, excessive moisture on the inside of windows or walls, chalky white powder forming on the chimney and vents, visible smoke obviously in the living space, are all signs and warning signs that you possibly have CO. High CO levels at light off may be an indication of rough or delayed ignition, warranting obviously further investigation. The CO readings will peak on startup, then dramatically drop. CO readings should stabilize within 10 minutes of operation and should never be rising during operation. If they do, you definitely have a problem. Mechanical problems and CO, if an appliance being tested has sufficient combustion air and is still producing higher than acceptable CO air-free levels, it could be a mechanical problem. Possibly maybe like a failed combustion chamber, cracked heat exchanger, something like that. Inspect the burner for cleanliness, proper alignment, fuel pressures, and evidence of any sort of flame impingement. Missing burner covers, improper air band adjustment, or oil pressures can also be a contribution to higher than normal CO levels.